In this lesson, we'll go through two examples on how to determine the basic shapes of molecules using the VSEPR theory. Question 1 reads, determine the molecular geometry of NO3-. Let's start by writing out the Lewis structure for this molecule. We have the central atom, nitrogen, and that's surrounded by 3 oxygens. So far, we have used up 6 electrons to draw the structure, but the total number of valence electrons can be found by taking 5, which is the valence of one nitrogen atom, plus 3 times the valence of oxygen, which is 6, plus 1 electron because of that charge. 5 plus 18 plus 1 gives us 24. And 24 minus 6 means that we have 18 more to work with. I'll distribute those 18 electrons around the oxygens. That's 12, 14, 16, 18. Now we know that nitrogen has a valence of 5 electrons, although at this point it's sharing 3 electrons. So we should have a set of electrons right here, and we can take it away from one of the oxygens. As you can see, I took it away from this. This has a complete octet. This does, and so does that, but this one does not. So we'll take these electrons and place them right there where we have N double bonded to this oxygen. Here's what happens. And now that satisfies all of the atoms. They all have a complete octet. And don't forget that the molecule had a negative charge. Now certainly this could have happened with this oxygen and that oxygen, so whichever resonance structure you choose, it doesn't really matter in this particular case, since they're all equally likely to occur. Next, you want to determine the total number of electron groups. Starting with the central atom nitrogen, notice that it is surrounded by one single bond, another single bond, and one double bond. Each of those counts as an electron group. So in this particular molecule, the number of electron groups is equal to 3. And based on this number, you can actually determine the geometry that minimizes the repulsions between the groups. It turns out that the geometry that minimizes the repulsions between the 3 is the trigonal planar configuration. Take a look at this chart. Notice that we had 3 electron groups, shown here, no lone pairs, 3 bonding groups, in other words 3 bonds, 1, 2, 3, and that means these oxygen atoms are separated by 120 degrees. So the molecule should look like this, where the angle from here to here is 120 degrees, the angle from here to here is also 120 degrees, and the same thing can be said over here. That's the answer to question number 1. Let's move on to question number 2. This time, they want us to determine the molecular geometry of carbon tetrachloride, this molecule. The central atom is carbon, and that's surrounded by 4 chlorines. What you see on your screen is the Lewis structure minus the electrons, which I'm filling in right now. And we can do the same thing as before. Let's find out how many electron groups there are. 1, 2, 3, 4. So there are 4. It will apply to one of these. There are 0 lone pairs around the central atom. That applies there. And the number of bonding groups, 1, 2, 3, 4, is shown there. That fits this row, and that tells us that the molecular geometry here is a tetrahedral. So it would look something like this, with that element being carbon. Each of these peripheral atoms, the chlorine, are separated by 109.5 degrees. And there you have it. 2 examples on how to apply the VSEPR theory when determining the basic shapes of a molecule.